this still works. But, I mean, the microphone still works. Okay, good morning. Sorry about this delay. They removed the computer. They actually made the system not even linkable to any other computers. So we have to reboot the machine, so finally it comes out. I think the screen is still smaller than normal, right? But probably it will work. If you cannot see it clearly, you can move to the front. Okay. So last time we discussed about many methods we introduced in a very high level, very brief way. We introduced the Bayesian belief networks, we introduced the neural networks, and support vector machine. Now we get into the rule-based and also the pattern-based methods. Okay. The general philosophy for this method is this. Okay. We actually want to make our classification model more readable, more communicatable to human. Because many of these people who are doing classification are the domain experts. For example, like medical doctors. Okay. They know a lot of knowledge. They want your model to be explanatory. That means at least that they can easily understand why you say this one is positive or this one is negative. And the neural networks or support vector machines give you lots of mathematical equations and parameters and different weights. Like a neuron, if you show a deep neural network with many layers hidden, and every layer, what's the weights? Nobody really can understand what's going on. Right? So then the one interesting approach which can make things explanatory is using rules like this if then, those rules. Okay. And for those rules, you can see is the interesting thing is if you have you have certain conditions. That implies you have some antecedents or conditions. People can clearly see, then you say, then something happens. Okay. That we call antecedents. You have, antecedents and the consequent putting together actually becomes a very good explanatory rules why you make this decision. Okay. Then the interesting thing becomes how we can evaluate this in a certain way. Okay. One interesting way is you can measure them using coverage and accuracy. Coverage means among the data sets, the so big data sets, how much you can cover. Okay. This is the coverage. That means if my rule can cover 20% of this data set, of course I made another rule and another rule to cover more. But at least you know my coverage is about 20% of all my training data. Okay. Then the accuracy means how many things among those covered are correct. It means I can cover the condition of 20%, maybe For 100 samples that cover 20, maybe 19 is right. One actual predict was wrong. Okay, so there's accuracy. That means 19 over 20, you get 95% accuracy. Okay. That's basically how to assess the rule. Then, if you have multiple rules, sometimes you got a condition. That condition may make 2 or 3 rules fiable or satisfiable. That means they may satisfy multiple rules. And how to arrange those rules. That means which rule should be put in the front. First, fire. That means while you hit this rule, and this rule makes a prediction, you think this prediction is right. Okay. So rule ordering is also very important. Okay. How to order it? Usually, you want to make the rule more specified to match. That means the longer conditions, the more conditions, the tougher to make the rule fire. Usually, you should put the highest. Just give you a simple example. If you say, these people will buy a computer, then you make a rule. You have one rule said, if this one is a student, you'll buy a computer. That's one case. Another one say, if this one is a student, make a good salary, or family is rich, or this guy got an A or something, then you'll buy a computer. So which one you want to put in the front? You want to put those more complete conditions to be satisfiable, put in the front, because that's more specific. Okay. You think about this. If you say the final score is A, then if you say you take CS4 12, you'll get an A. That may not be true, right? But if you say you take CS4 4.5 for 12, if your score in midterm is over 85, you'll get A. That's a more specific, likely, the more specific rule will be more accurate because match you. It's tougher to match you, but once you match you, it's more specific, likely will be right. Okay. So that's the first thing is size ordering. Another is class-based ordering. The class-based ordering means you may say sometimes you misclassify the cost is higher, or just thinking about those cancer case. Okay, sometimes you may say if there's a suspicious to be cancerous, you put this one in the front. Why? Even you get false alarm, probably false alarm is better than no alarm. Right? If you really got cancer, and the rule said if you're okay, then you may delay your treatment. Right? So that means that class-based can be ordered. Like more important case, class put in the front. Okay. Another could be a decision list. That means rule-based ordering, based on some complex rules, like values or priorities or likelihood or something. Based on this, you pick up the most important rules put in the front. Okay. So those are different. That means you have a rule-based, you generate many rules. You may want to order rules in a smart way. Now we look at decision trees. Remember the first one we discussed is decision tree. Okay. Decision tree will generate many rules like this. These rules actually, the first thing is if you use decision tree, the rules are reasonably compact because your decision tree is from many, many real data, very concrete data, you generate a more compact tree. So compact tree means a small rule set. Another interesting thing is the decision tree, if you look at the tree, they are mutually exclusive somehow. That implies you do this, you can fire in any order because they are mutually exclusive. They only lead to one decision. Okay. But some rule-based system, we generate many rules. The rule may be overlapping. Some facts may satisfy multiple rules. Okay. The rule may give you different conclusions. Okay. Then, for rule induction, there are many methods how to derive rules from your training data. Okay. A very popular method called sequential covering method. For this method, I'm not going to give you a lot of detail, but I actually put 2 slides as hidden slides. But if you download it, you actually can see the 2 slides. The 2 slides I will not lecture in the class. That means it will not be covered in the exams. But it's nice to know it. That one gives you a little detail on the sequential covering method. Okay. The sequential covering method means you, from the big training data sets, okay, you try to derive one rule at a time using some kind of evaluation method. What are the evaluation methods? There are quite a few, like Fourier, AQ, CN2, Ripper. There are many such methods. Actually, in the hidden slides, I will not present in the class, but you can still read it. It's the first one, Fourier. It was still done by Ross Quinlan. Okay, he worked out some kind of information gain, like they call Fourier gain. Okay, based on this gain, and he can first grab a rule which can satisfy some portions of training data in a reasonably smart way. Some kind of information gain computation, compute the Fourier gain. Okay. Then he learned one rule at a time, then said that this part data is already covered. Then look at the remaining data to derive another rule, cover more data. And finally, he can cover almost all the training data. Of course, some rules still overlap. Okay. So that's his sequential coverage. Sequential means you cover one at a time in sequence. Then you finally can cover the whole training data sets, training space. It is an iterative loop. So decision trees learn a lot of rules simultaneously, but this sequential covering is to learn one rule, you take that data sets covered out, then you learn another one. Okay, it's a different one. Then when you apply it, you also may follow some kind of order instead of like a decision tree. You can apply almost in any order. Okay. So, but we are not going to give you a lot of detail on the sequential covering algorithm because nowadays it's not used so popularly. Okay. Decision tree is still used quite popularly. Okay. Now I'm going to introduce a little newer method called pattern-based classification method. The pattern-based classification method, general philosophy is we already learned the frequent pattern mining. Okay. Those patterns are very useful because they actually get from your massive data getting into you draw those frequent patterns. Okay. But a frequent pattern itself, just too many. Okay. So people actually found if you want to do good classification, you can use frequent pattern, mined pattern, organized in certain order. Okay, then you can work out a pattern-based classifier. Okay. The general idea you can think is the pattern-based classification, different from the decision tree, is you work out frequent pattern, not one feature at a time. You combine them. Remember the pattern, you say frequent 1, frequent 2, frequent 3. You're enlarging your length or width. That means you use multiple things getting together to make an induction or a conclusion. Thinking about it, say, what condition you will get an A? They may say, you first say you must take CS412, of course. And you must do all the homeworks or exams, of course, otherwise you will miss some scores. And then you must do something like reasonably well on the midterm and do some project and do something on the final. Okay. If you say this, you are working out multiple features. That means taking CS412, did all the homeworks, and did it the midterm and did the final. Okay. So those are the things you can see. You get a multiple feature combined. Okay. Then you can get something. You actually can see sometimes a single feature may not be that good. For example, okay, to give you this, suppose you say apple. Okay, you put apple there. It could be ambiguous because you get apple pie or apple computer, right? Like this one has an apple here, right? So, but you probably see once you put more things, you say apple pad, iPad, or then it's not about apple pie or pears, right? Bananas. So in that sense, single word is not ambiguous, but you put more features in, it becomes much sharper. Okay, that's also the general philosophy. Sometimes you may even get sequences or graphs, okay, those complicated structures to make decisions. Okay. Just to give you a simple example. Okay. So, for example, if you want to say what kind of chemical structure may have some treatment effect, okay, then what you see here is you can decompose your complex structures into some kind of substructures. Like you have a band ring or some kind of ring, and you have the other one. Getting together, you can make some decision. So that means substructure pattern mining, getting patterns. You combine these several patterns together, you can say, I can make a good classification. Okay. Now, we probably will show you a few interesting things. I'm going to show you a few algorithms. Actually, these three algorithms are also introduced in my Coursera online, massive, those MOOC courses. I put three essays to be discussed here. That implies these three algorithms I'm going to introduce it. Okay. Actually, I'm going to introduce you one more, which is a very late one. It's published this year, 2016. Okay, but I'll introduce you at the end of the lecture. The first one was CDA, was Bing-Liu's method published in KDD 1998. Okay. Bing-Liu's method, actually, Bing-Liu is a professor in University of Illinois, Chicago, okay, UIC. But he currently is a CKDD, this ACM special interest group. He's a CKDD chair. Simply said, in the KDD community, people elect him to be the chair, okay, for 4 or 5 years term. Okay. So let's look at his contribution when he was a professor in Singapore. Okay. What he did is this. Okay. He actually got association rule mining. But he says if you take association rule, put all the class label at the right-hand side. Okay. Put a class label at the right-hand side. For example, you say buy computer or not buying computer. That's a class label. Okay. Buying computer, yes or no. That's a class label. Put on the right-hand side. Then you put all the other things in your association rule mining, or the other things at the left-hand side. You actually form a classification rule. Like what condition, buying computer or not buying computer? You have support and confidence. What he did was this. He actually say, because the confidence means the chance to buy a computer really high, he ordered all these association rules first according to the confidence. For example, he said, under this condition, buying the computer is 99.5. So he will put it 99.5. And the other condition is 80 or 70. He will put it sorted according to the confidence. Then if they have the same confidence, he will sort according to support. They have more data to support this confident one, this one will be the higher priority. He sort this. Just based on this, he constructed a rule-based classifier. He showed his rule-based classifier just based on association rule mining using the sorting. His classification accuracy is comparable, actually it's more accurate than C4.5 decision tree method. He did not use information gain, just use association rule mining. That one really surprised everybody. We were thinking your association rule mining is nothing to do with classification. Now he shows it actually can be very good. Okay. And that paper actually cited very popularly. And I think last year or year before, the paper got like a highest impact paper award in the KDD. Actually, among the KDD history, they actually found this paper is almost the most cited paper, or second most cited paper in the KDD proceedings. And after this, okay, I got a student, George Lee, in Canada. That time, he read Bing-Liu's paper, published in 1998. He fears this, just plainly sorted by confidence and support is a little too radical. Okay, because sometimes you may have a few, for this particular testing data, you may have a few rules, both fireable. That means both can make a decision. If you're strictly based on confidence and support, maybe their confidence very close. And the support, you first sorted by confidence. One said 99%, the other said 98%. But what about they make a different conclusion? Okay. One said that this one will win, the other one said the other one will win. Then finally, you need to look at the support, right? That means who covers more data sets. You cannot just based on this. And what he says is he wants to collect reasonably high confidence one. He collected those, a set of rules together. Then what he did is he took this set of rules, he divided based on the class label, divide to say yes or no, get two classes. Then based on this condition, he actually worked out a weighted chi-square measure to find the strongest group of rules to make wiser decisions. Very simply says, if you think of Bing News method basically based on first the source support and the confidence, sometimes, similar support, similar confidence, you get a very different support, you actually miss it. And his method actually a little more scientific in the way. He group all those satisfiable rules based on their class labels, and then doing this chi-square measure analysis. Okay. And finally, he shows his CMAR, this method, actually is a group of the rules-based analysis is better. Okay. That's about early days. Then we got another very interesting paper by Hong Chen. That time she was a PhD student here. Okay, now she is a professor in Chinese University of Hong Kong, in Hong Kong. Okay. And she made a very interesting study in this. She just say, people always say there are so many measures, information gain, Fisher score, there are so many different measures. And she just wants to see where the real gain, like information gain or Fisher score, where the highest one potentially resides in what kind of attributes. Then she made a very interesting observation. Just show you this graph, you probably can see. She actually took the machine learning repository in UC Irvine. Okay. There are like almost 100, now probably more, data sets. They have training data, they have labels, there's all the real data sets. She took many. She tried to study where are the information gain stores. That means where are those attributes contain highest information gain. Just based on information gain analysis, she worked out this graph. It's very interesting analysis. Okay. The first thing is she looked at the single attribute. If you look at down part of the first line for every data set, like this Offshore, Cleve, the Sonar, those are all the different data sets. She studied all these data sets. First, she wants to study where are the high information gain, where it hits. Okay. The interesting thing is if you look at the leftmost line, it's a single attribute. Remember, the decision tree always want to grab the single attribute, then make a decision to split. Okay. She took the single attribute, look at the information gain. To everybody's surprise, the single attribute, no matter which data sets, the high information gain is very scarce. You look at the dots, means information gain points. You want to find high information gain, the single attribute actually cannot make good decisions. Okay? So this is more like you think about it. You cannot use one variable to make a decision. Right? And she actually saw if you pick up a single one, you combine into two attributes at a time. Okay, that means two variable analysis. The information gain, you see, no matter what data, the information gain, the high one immediately become much more. You can see those high information gain one become much more. Actually, this phenomenon not only confined to two variables. You look at 3 variable, 4 variable, This 2, 3, 4, you look at the data sets, all pretty high. Okay? But you make it too many variables, you see they start dropping. That implies, okay, you have to use multi-variable analysis, not use single variable. Okay? But you just cannot use too many. Too many actually may not give you that much information. The information gain actually will drop. That gives everybody a single hint is why the decision tree may not make it that high, why Bing-Liu's method, those association rule mining actually can beat C4.5 easily, because the association rule actually uses multiple things. You say A and B and C implies fine computer, not just one, right? You actually, even you use decision tree, you start splitting. You say, just based on this variable, based on this data is split. Once you split, the data becomes smaller. Your training set becomes smaller. Actually, it may not be that good. And if you combine them together, say these three variables together, you'll get something. And sometimes it's very accurate. Okay. So you can see that's a general phenomenon for almost all the data sets. Okay. And another thing she found is the frequency. Okay. She studied information gain again. Actually, she studied other measures like Fisher score as well. If you go to her paper, she did a lot of in-depth study on all these different data sets. This one is about frequency. You still pick those data like Astra, breast, sonar, those real data sets in UC Irvine repository. What she studies is she wants to see the information gain relationship with frequency. That means if the pattern becomes more frequent, whether the information gain will be higher or will be lower. Okay. Of course, not everything frequent will be higher. But you can see, if you look at this, the frequency is x-axis, the information gain is y-axis. What you see here is the low information gain for the only one variable. Actually, the low information gain is quite a lot. Okay? But the high information gain, actually, you can see the frequency becomes higher. The information gain sort of also become higher, right? You can see the trend. When the frequency becomes higher, the information becomes higher. But it cannot be too frequent. Okay? You can see when it becomes too frequent, the information gain drops, becomes very scattered and drops low. Because too frequent, you think about it even when we do the text analysis. Too frequent means a stop word. Okay? Like you have if, then, or on, or off. Those things doesn't give you any idea what this paper is talking about, right? But you make several things getting together, what the paper is talking about, it becomes quite good, right? To that extent, you can see the information gain also needs something frequent, but not too frequent. So then she basically say, if you want to build a good classifier, you need to use a multiple variable analysis and a reasonable frequent. That means she basically say we need to use frequent and discriminative. Discriminative means, it really can have the power to separate classes. She basically proposed, if you want to do capture good feature, you want to capture those features as frequent and discriminative. Then use those features to do classification. Based on this study, she actually worked out, I should say, this resolution is definitely worse than our normal computer one, because the laptop probably doesn't match this projector so well. Really unfortunate. Next time, I probably should ask them to fix it quicker. Otherwise, it will really affect the quality of our class. But what I told you could be this. Okay, the next time if you have a computer, you can just read your slides instead of this slide is a little too blurred, right? But what I should say is, if you look at all the different rows, UC Irvine data repository, the real data sets she actually picked up. Okay. Then she actually used two methods to show the power of frequent discriminant pattern mining. She's not using like a CMAR or CBA, those kind of association rule mining, get association rule. What she got is frequent pattern. Actually, she got a frequent and discriminant pattern. That means not only frequent, but also discriminant, have high information gain. Okay. She took those patterns, then she said, my pattern can fit into any classifier, the classifier will become winner. Okay. What she did was the left-hand side is feed into SVM. The right-hand side is feed into C4.5. That means C4.5 SVM, originally they just took all the data. Usually they do single variable analysis like C4.5, do decision tree analysis, take every attribute, compute the splitting point, and get everything. Yes? You mean the item RBF and item FS? Yes. Okay, I'll explain this. Okay. You look at the left-hand side of the paper. The one with a single feature versus frequent pattern. Okay. Single feature means every time you take one feature. Okay. And how to take one feature, there are several ways to do. Okay. One called item R. The other called item FS. The third one called item RBF. Okay. Item R means you take all the items, single items, you feed into the support vector machine. Okay. Item FS means I only take the frequent sets. But I take all the frequent sets. You can see the first one is take all the items. The second one is take all the frequent sets. That means I set support threshold. If you are frequent, I take you. You are not frequent, I drop you. Okay. The third one said item RBF. RBF, remember for support vector machine, there's one called RBF. That means radio-based filtering or something. RBF is a kernel method. You actually can use RBF kernel to select more important features. So it's a very influential feature selection method for SVM. Okay, we call it RBF kernel. Okay, but she basically using RBF kernel to select something. Okay, select those features. So there are three ways to do SVM. Okay, you can see for a single feature. Then the other one is frequent pattern. Okay, frequent pattern. One is use all the frequent pattern feed in. Okay. Another one is using frequent and discriminant pattern to work out to feed in. Then you can see almost all the winners. So both printed font were her method. Her method means she first took a frequent, longer pattern, not single feature, but multiple features, and took in a frequent discriminant pattern mining, took those features. Okay. Those features, she feed, the first one feed into SVM. Okay. The second one is feed into C4.5, those published open source, like decision tree method. She basically feed this, and she shows if I select those features, frequent discriminant pattern, I always can enhance any classifier, including the pro-vector machine, including C4.5, including others. Okay. So this is a pretty interesting study to say you need a longer features, not single one. Okay. And longer feature, you need to do frequent discriminant mining to do that. So that's a very interesting study to see how to increase the classification quality. Actually, this is not C4.5 extension. It's just to say C4.5 originally treated every single feature as the known feature and feed into C4.5. Now she's not feeding C4.5 in that way. She takes the training data, first do frequent and discriminant pattern mining, getting those high-quality features, which many are combined features, like lens, not lens 1, but lens 2, lens 3, lens 4, those combined features. But those patterns are frequent and discriminant. Take those, you feed into C4.5 or support vector machine, whatever you feed in, you enhance their classification quality quite a lot. Okay. So it simply says, not only the classification, you need to use better features. You need to use combined features, multi-variable features. Okay. But why previously the multi-variable feature not used in like a statistics and machine learning? Because the multiple features, combine them, you easily got it. You explode your feature space. You think about this. This feature has 1,000, different distinct values. The other one you have 1,000. The other one you have 1,000. You time them together, you get a million. Okay. How could you handle those 1 million features? So that's the reason they don't use it. But you do frequent discriminant pattern mining, you get smaller sets of features, much smaller. Then you feed them in, you see the power. Okay. Even lens 3, lens 4, right? But most other people cannot do it because you're just thinking about it, just too many. You time everything together, just too many. Right? So that's a very interesting study. And later, she actually used this method, work out a directly mining frequent pattern, because originally is you first mine all the frequent pattern, you try to select them. That's still very expensive. And she actually worked out another method called DDP mine. Okay. It basically is mining this one directly in an efficient way. Okay. Another interesting thing is people were thinking you have to use a lot of features to do good classification. She actually showed if you really do frequent discriminant pattern mining, use very small number of features, you probably still can do very good classification. Okay. So she showed is this. She based on 2 data sets, one called waveform, one called chess data. This is also from UC Irvine machine learning repository. Okay. And she actually used the minimum support to cut the number of patterns you have to mine, you have to feed into classifier. You probably can see the first one is number of patterns, time, SVM, and C4.5. SVM means you feed into SVM classifier. The other one means you feed into C4.5 classifier. Okay. Then you can see you can use minimum support to cut data. If you say minimum support is 1, you see everything says no, not applicable. Why not applicable? Because supported 1 means every pattern you appear once you were counted. You just get too many. You get millions or billions of them. There's no way anybody can do any classification. So even cannot generate all the patterns. Okay. But then you raise to minimum support 2,000. Okay. Then you actually can see you generate 68,000 patterns. Okay. Of course, it will take much longer time to do it. You get 92%, and the other one 97% accuracy. But she says, instead of I use 2,000, I raise it up. She actually raised up to 3,000. Then you get much less pattern. You get only 136 patterns. Then, of course, raise it up, the mining time is immediately dropped to 0.063. Okay. Then you look at the classification accuracy, actually did not really drop much. You even compare with the 2,000, it's very comparable. That means you still get a pretty good classification accuracy. But you use much less patterns. You take much less time as well. Okay. So that's one study. The other study you probably can see, using waveform data, she actually used minimum support 1, she generated 9 million patterns, then immediately blow up all the classifiers. So then forget it. But she used 80, minimum support 80, she got 26,000 patterns. She got certain classification accuracy. Even she raised to 200, get only 2,000 patterns. Take 8 seconds. It still get a pretty comparable accuracy. Of course, you use less pattern, maybe it may not be that accurate, but still quite good. Okay. So that implies the frequent and discriminant pattern really give you some power. Instead of using single features or all the combined features, which is not realistic, she does use combined feature, but in a selective way. Okay. So that's a very good lesson. Okay. But then, okay, this even distorted a little. I do not know what whether I should show you the whole thing in the other way. Is that better? I mean, just because it's a different system, then you got different. One is on the Apple, one is on the Microsoft one. They are not comparable. Okay. Hopefully, we still can see it. Now, this time we can see it. It's mining concise set of discriminant patterns. Okay. Actually, this one was the most recent one. Hong Chen's work was published in 2007 and 2008. In 2016, okay, our group actually not doing, after her graduation, nobody was working on this. But she still worked on this in Hong Kong. She worked out quite a few papers. But in 2016, we got another PhD student. Of course, currently, he's still a PhD student here, or Jingbo Shang. He is still a reasonably young PhD student. I think this is his third year. But he got this paper really, really interesting at this. He looked at a lot of patterns. The problem is you can see from Hong Chen's study, you generate a reasonably good classifier, but may still need thousands of patterns. Okay? Thousands of patterns for, say, physician. Okay, suppose you give a medical doctor, say, I can judge, whether this guy got cancer or not. But you still have thousands of rules. Okay. You think the doctor would like to use it? Even you say it's explanatory. But you get thousands of rules or millions of rules, and people read it, and nobody wants to read the thousands of rules. Okay, that's pages over pages. And he was thinking, if we really want to generate a rule-based classifier, we need to generate very compact rules. For example, if I said maximum number of rules is 20, that means I can fit into a Google like almost page 1 or page 2. Probably the doctor would say, that's great. I would like to read it. Why you make this good classification? Okay, because 20 rules anybody can comprehend. How can we reach this goal? Okay, that's a very hard problem, right? Because you see frequent discriminant pattern mining already got thousands of rules. And you perceive that's Hong Chen's work, DDP mine. What she did was directly mining a discriminant pattern, which is very efficient. You generate actually from the almost 10,000 to millions rules. She actually can generate something like about several hundred or 1,000 rules. But Shang actually he got this. He says, I want to generate a very small number of rules, but still get a very high quality classification. And we do that. Okay. Then she worked out a very smart method. The method was using random forest. Okay, that's exactly I want to give you the homework. Say we have to do, one is decision tree, one is random forest. Your random forest, even you think a random way generated so many trees, actually could be very useful. Because every tree has certain classification power, but you have a limited training data, you use a random way, you actually cover many corners. Then what he did was this. He says, I got this training data. What I do is I take the training data, I use random forest generate a bunch of trees. Okay. Then sometimes generate too many trees. It's still no good. You give the doctor said you use so many trees. Each tree has essentially contain many roots, right? That's not good. What he did was he took the tree, he looked at the quality pattern on only sub-branch of the tree. Take every branch, even not touching to the end. The branch you stretch, you can touching to the end, but the data becomes smaller. Right? If you think about the tree, you generate a certain tree, you have some good classification capacity, even not to the end, you still have this tree generated, still have some classification power. Okay? He took many such branches. Each branch, he thinks this is the feature. Okay? Then he took those features, he actually get into a regression model or some kind of logistic classification model, and only take those sub-branch tree as a feature, combine them, select them, combine them, to see whether he can generate a good, you can say, good rule set. Okay. That means he wants to see the different branches. He gives different weights. Okay, say this branch I found has classification power. If I combine them, this is 0.1, this weight 0.3, the other one maybe weight 0.2. He combined this, generate a rule, say this rule has good classification power. Okay. Then what he finally show is, if I confine the number of rules you can get, it's just 20. That means you have to use 20 to cover all my training data, and with good quality of the classification, I pick up this 20 rule. He only used this method, but he shows if you run this top K to pick up top 20 rules using the pattern selection and combination, you train a generalized linear model, which usually, for example, use logistic regression to train it. That's why I actually did not give you this method to ask you to do homework, because some people may say we did not cover logistic regression or generalized linear model. So I just say, I told TA, forget it. Don't give students more work. They have to read a lot of papers. We just ask you to do random forest. But you probably know why we want you to do random forest, because you use so popularly, including this work, also use random forest. And actually, we have a very good phrase mining methods, or set phrase, also using random forest as a class. So it's very popular use. So, but we take this, train a generalized linear model, take top 20 rules, we get a bag of patterns, we can represent the whole training data set, and that training data is really, really compact. Okay. So the important thing is it has good explanation power just because the rule is so small, so compact. Okay. Here, he just give you one simple example. Okay. Like you think about it, suppose this one is a patient database. You want to classify whether the patient has some particular disease. Okay. Then what you do have labor data. Okay. Like here, this case is, they want to categorize the label, the test data. You can have age, gender, labor test 1, labor test 2. You can see labor test 1's category data is your blood type, like A, B, O, or A, or AB, those kind of blood type. The other one is continuous value based on your lab test. Okay. Taking this, and he can work out many those kind of patterns. Say, if age is greater than 18, gender is male, or blood type is AB, the other test is greater than 0.6, that could be like one condition. That means these are the 4, you can think 4 features combined together as a lens 4 feature. But that's definitely makes sense, right? You have to combine them for doctor to say this likely will be some problem, right? So, and he training is 10 to the power 5. Okay, unfortunately, this one is a Mac. So once you show this, you probably know the Mac show to the power. It's just to put an outside arrow. The 10 to the power 5 random patients with 0.1% noise. You can flip the binary data with this probability. The test data is 5 times 10 to the power 4 random patients in the test. That means he actually used a lot of patients from the training data and from the test data. Right? He worked out the rules like this. You can see those are the rules. And the rules he shows, his method called DP class, discriminant pattern classification, DP class. Okay. You work out rule, these red one rules, you got like 99.99% accuracy. Okay. And he actually tried a Hongchen software, DDP mine. Sometimes the DDP mine may generate pretty poor rules, like pretty short, but the accuracy may not be that high. Okay. And it shows DDP mine generate 95% accuracy. It's still reasonable, but you need much more rules. Okay. So then he actually did a lot of very interesting ones. Let me see. An interesting one is, you probably see these, they are ucrtn data sets. Some part is low dimension data, like adult, hypo, sick, CRX, SONA, chest. Those are low dimension data. And some are high dimension data. You can see those are high dimension data. Then he actually shows he has two DP class classification methods, one called forward classification, one called lasso classification. Lasso is a statistic analysis package. I'm not going to introduce it. You basically know this needs some kind of statistic calculation. Okay. But he basically used this tool. Forward is pretty simple. The lasso is a little more complicated. Then he actually showed the DDP mine, this home trans pattern-based method, and shows the random forest method. That means you generate lots of things. You just use random forest to do it. Okay. Remember, both random forest and the DDP mine will generate a lot of rules. The model is quite big. Okay. And his model is very small, like 20 rules. Like you probably can see each rule is not that long. You get 20 rules, right? And you see his classification accuracy comparing with the others. Actually, it's not that at all. In many cases, it's the champion. Okay. Of course, in some high dimension data, you still see the random forest does have edge, even generate a pretty big model. The random forest is still good. But the model is too big for the doctors to make a decision. Right. Yes? Yeah, your question essentially is, since we say top K, you probably get generate reasonably large set and to do selection, right? You probably can see is you do generate a bigger one, you finally get top K. But since you generate this random tree, random forest, you select only sub-branch, those branches, sub-parts of the branch. The number of things to do the combination, of course, is still many, but it's still limited because you combine those things. So finally, you rank them, you take top K. In his paper, it does show the running time actually is pretty fast as well. It's not that of course, you still finally generate reasonably large, you select the top ones, the high accuracy ones, based on the testing data. Right. Remember, we still have lots of test data. To test it, you see which one gives you better accuracy, you select them. Okay. And the very good news is the pattern finally generated is very compact, like 20 rules. So everybody would love it. I actually have, there are two stories. One story is Professor Bruce Schatz has a PhD student called Tian Cheng. He did his PhD on, people get heart problems, then they walk, they can, based on their walking speed or something, they have the iPhone. Based on this, to suggest the exercises. They have the classification model. They collect the real data on lots of patients, how they move. Okay. And they try to construct decision tree to give advice to patients, what they should do. And they got this data. They tried many classification models. They have a testing data. They have labored. They have a training data, labored, and testing data also labored. They can see which one give you better classification. And this home train tried many classification methods. Okay. Once he wanted to schedule his PhD preliminary exam, he came to me. He said, I tried many models, SVM, decision tree, random forest, many models. He got work out this. He said, do you have any suggestion? I say, you try this newer one. Okay, you try it. And he tried it. He found very accurate. And also the pattern generated, the rule generated, is so compact, so small. He can go back to talk to those car doctors or any professor. In a very, very short rule, he can explain how you should do it, what case you should do, what kind of exercise. He found that this one is really great. And then he actually took that one, look at those cardiopulmonary rate. This means that the heart, people can hardly move, and how to suggest people doing exercise, those patients. And he take this and some work out a paper and send to the conference, which is this year's ACM. I think this is bio or some healthcare, those forums. Okay. And they really love this paper. They say, oh, you can generate so small rule and get so high accuracy. They immediately took this paper. Okay. And he finally got his PhD. Is mainly he used this one to show his previous study in the preliminary study compared to his new study using this method. This one is far better. So then he already graduated just 2 months ago. I already loaded his paper into our publication website if you want to read it. And another interesting example is somebody industry came to me, said currently people working on deep learning, work on so many different classification models. The DARPA, the Defense Department, they wanted people to work out explanatory machine learning. Explanatory means you want to generate the model, people read it, they can be explained. Okay? Because a support vector machine or neural network or those things, they generate this thing. It's so complicated. There's so many parameters. How could you understand it? Okay. Then they came to me, say, do you have any suggestions? I gave him basically 2 papers. One is University of Washington Gerstein's paper, which this year, KDD 2016. They can change the model into rules. Okay. I give him this paper. I said, this is very interesting. Another paper is this paper. Okay, this Jingbo Shang's paper. They study it. They say they really like Jingbo's paper. They want to write their proposal for DARPA, mainly based on this one. Okay, so people can see. The industry, they got discussion, they make judgment. They really like this work because they think it generates so compact and so accurate rules. The rule is so small. If you use the University of Washington approach, when you generate rules, the rule actually, the accuracy is not as high as the original neural networks because you try to compact it, you have to make some approximation. And this one, you directly get this rule. It's really explainable. You probably can see the power. I strongly suggest anybody later go to industry. You want to really generate a compact explanatory model, you think about this paper. This paper really. Actually, he got further on the prediction one. He worked out another paper currently under evaluation. The one can do the regression using the same methodology. And it shows last year we had one student actually win the award on the data challenge for some bio competition. Actually, this one likely can improve it. They currently are studying this one. I think we have one student actually win the award in the class. So, but anyway, this one is a very powerful one for rule-based classification. Now you probably see we got a rule and pattern getting together can do strong classification. That's very interesting. Then there are other classification methods I'm going to introduce in the next several slides. One called lazy learner and a k-nearest neighbor classification. What is lazy learning? Okay. Lazy means really lazy, right? In the sense, all the other people doing things called eager learning in the sense, you give me training data, I start working on this training data, try to work out a model. No matter I build a neural network or I do my decision tree, or do rule-based, whatever, I work on this thing. I work out a model. I'm waiting for you to give me any testing data. I can show you my model, right? But lazy learning say, I don't work on it. You give me the training data, I sit there, I sleep, okay? So when I want to do things, is when you give me the testing data, you say, here, what is the label? Whether this tissue is cancer or not. That's the time they start working on the training set. How they work on the training set? One popular method called k-nearest neighbor. Okay, I'm going to immediately introduce you to this k-nearest neighbor, but I first do a little hand waving. Okay. K-nearest neighbor means you give me this testing data. You say, this tissue, whether it's cancerous or not. And this guy does not build any model. What he will do, he will say, this cancer, this tissue, you get several features. I try to find in my training data what are the closest thing, closer to the thing you give me. Okay, that means you said, how many blood cells or how many something. I try to find the similar data sets in my training set. Okay, then what I do is I took those training data sets, I look at their label, I ask them to vote. For example, if this training data, I look at the nearby things, I found this training data, there are 5 set of cancerous, 1 set of no cancer. Likely, I would say, there are 80% chance to get cancer. Okay, so that means he does not have any model constructed. But he instantly just check his neighbor. Okay. Actually, it turns out that sometimes the lazy people may have some edge. Okay, sometimes those lazy learning, those k-nearest neighbor, get a very good classification accuracy. So next lecture, I'm going to discuss those kind of classification methods. Okay, thank you.